Okay, so in this last video, I want to look at absolute continuity from a deeper perspective. So just remember the definition. F is absolutely continuous if for any epsilon there exists a delta, where if we have a disjoint collection of intervals in A to B where the sum is less of some of the lengths is less than delta, then the sum of f of the difference of endpoints is less than epsilon. Okay. Okay, so a deep fact. Well, one direction is not too deep. The other direction is very deep. F is absolutely continuous, 0 to 1. If and only if F prime exists, best we can do is for T for almost every T in 0 to 1, sorry, A to B. Not only that, but F prime is integrable. And probably most importantly, the fundamental theorem of calculus holds. So I believe this is due to Lebesgue. The guy is pretty famous for a good reason. So yeah, this is proved in the early, I think the 1920s maybe. So for any x in A to B, we have f of x equals f of A plus A to x, f prime of t dt. Okay. Yes. So okay. So the easy direction is as follows. So let me that. So let's call this star. So easy direction is star implies f is absolutely continuous on A to B. So first I need a lemma, and this itself was actually proved. This is actually a prelim problem itself, this little lemma here. I have 4 prelims here. Which one is it? Yeah, so I'm going to prove this here. And this is very easy using the density of particularly, you don't even need step functions in LP. So I'll actually do this for, yeah, I'll prove this for any E. So I'll make a different statement. So you don't really need density of step functions. Density of simple functions is enough to do this. Okay. So yeah, this is August 2023, problem 1. Let's go back. Okay, so in general, if E measurable and F is an L1, so not a terribly surprising result and not a terribly difficult proof. Right. So for any epsilon bigger than 0, there exists delta bigger than 0 such that for any A and E, measure of A less than delta implies this is less than epsilon. So you have 2 options here to prove this. they're both just as quick. You can either do Borel-Cantelli. You can assume this is false, and then set you get an epsilon 0, and you can set delta to be 2 to the minus n. Probably much easier, admittedly. As much as I like Borel-Cantelli, it's just to work with density of simple functions. Okay. Pick epsilon bigger than 0, and pick g is, let's say, I equals 1 to m, ci characteristic function ei. We can always do this where the EIs have finite measure. We don't even care about that. Let's do epsilon over 2. So A is a subset of E, and this less than delta implies this is less than or equal to this here. What is less than or equal to L1 norm over E? Just replace A with E. And so this is actually going to be equal to G times characteristic function of A. So I'm going to smash in, I'll do it like this here. We've done this before. Multiply both sides by a characteristic function of A. And so this is going to be characteristic function EI intersect A. So this is going to be, and I'm just going to smash in absolute value. I equals 1 to, sorry, I haven't even picked delta yet, so that's a little, I'll pick delta in a minute. We'll see where it comes from pretty clearly. Yeah, so we have to figure out a delta where this works. So this is I equals 1 to M. M is M. With A intersect EI. Yeah, well, it's a subset of A, obviously. So this is less than or equal to epsilon over 2 plus sum I equals 1. Yeah, so it's just a measure of A. Okay, so one thing is, so yeah, we're basically done if G is 0. So if all these of all the C's are 0, then G is 0, then there's really nothing to prove. So let's assume that yeah, I mean that basically if G is 0, then that's saying F itself has L1 norm less than epsilon. So then certainly this is going to be true. So that lost generality. The max is not 0. Let's say delta is anything. So let's say delta is epsilon over 2 times this sum here, and sum is not going to be 0. It's a finite sum because M is finite, And it's nothing, there's no, the sum is not zero. So yeah, so now we're done. What we had before, epsilon over 2 plus this here. It's just less than epsilon. So very easy proof using density of simple functions in L1. Okay. All right, so yeah, with that out of the way, let us prove this. And this is actually really not much to it. So yeah, I'm going to prove so proof star implies absolute continuity. Remember, star is all this. This exists, f prime is now 1, and fundamental theorem holds. So pick delta as in the lemma. But instead of for f, I want for f prime. Yeah, f prime is an L1, so I'm going to use the lemma using f prime. And E is A to B. Right. Okay. So if each one of these is a subset if each one of these is a subset of 0 to 1, or A to B, I keep saying 0 to 1. And if this sum, sorry, it could be infinite, but it not be. So if this sum here less than delta, then set A to simply be this disjoint union here. We're almost done. So this trivially is less than delta. Okay. Okay, well, let's figure out what this sum is. Okay, so this whole thing here, using the fundamental theorem, is going to be f of bi plus a to bi prime minus f of ai sorry, 1 second. Sorry, it's f of a. Yeah, otherwise that makes no sense. It's really funky. Minus f of a as neat as possible. So it's minus f of a minus a to ai f prime. All right, so this of course just equals, well, these cancel, so it's just, and minus makes it a plus, but you switch it, so AI, BI prime. So I will smash an absolute value in a moment. So this is not subtle stuff here. The other direction is very subtle. Okay, well, this equals because this is A is a disjoint union of these intervals. This is going to be equal to the integral of A prime. That's less than epsilon because we picked delta in the way where measure of A is less than delta, and A is a subset of 0 to 1, implies that the integral of the absolute value of f prime over A is less than epsilon. So basically the same proof, and I'm not going to go through this. I went through this actually today in Zoom. The same proof proves that it basically does 4A. 4B is almost the same actually. But we've basically proved 4A, if you think about it. And I'll leave that for you to do if you weren't there or whatever. So basically same argument because we're assuming f is a big integrable on 0 to 1. Same argument says that big F defined as this integral, almost the same problem. Almost the same arguments tell you that big F is absolutely continuous. Okay, so this is working. Okay, so another problem that uses this is the following. Prelims up here. Is this? Yeah, it's this last one here. Go 100. Let's go 100%. Okay, so let's do B. So 7A is, you can even use what we just proved for 7A, because the interval, the interval 0 to x, when x goes to 0, that length goes to 0. So you can just set A to be 0 to x for basically x less than delta, or use Dominic convergence theorem for 7A, either one. So I'm not going to do 7A, that's an easy exercise. So 7B is kind of interesting. And so when I did this when I wrote this prelim, and I did write it with someone else, I remembered that I did not go over absolute continuity. So that's why I gave you this hint. But if this was in a future prelim, you would not get this hint. So let's do this. Let's say H is absolutely continuous, H of 0, 0, and H prime is an L2. So actually it's a little bit mean. This was not my problem. This was the other writer's problem. It's a little bit mean to not tell you what the limit is and just tell you to prove it. But this is actually going to be 0, so let's prove it. This is a really, really, really clever use of Cauchy-Schwarz inequality. You do things like this a lot in research, as elementary as they may be. Yeah, I'm going to end everything off with doing this problem. It's a nice problem. I think that is it. Yeah, that is it. All right, so this is January 2024, 7B. All right. Okay, so yeah, so we're going to first use the fundamental theorem of calculus because telling you that it holds for absolutely continuous functions. Okay. So by absolute continuity for any x in 0 to 1, h of x is going to be equal to 0 to x, h prime of t dt, less than or equal to 0 to x. So I'm going to write this in a funky way. I think I could fit it. 0 to 1. So it's silly, but there's a reason there's a reason why I'm doing this. So multiplying the characteristic function twice does nothing. But I'm going to use Cauchy-Schwarz Holder's inequality with p equals 2. And I want both to have a characteristic function here. So of course, integrating 0 to x, same thing as multiplying, by definition, actually, is multiplying by this characteristic function. So I'm going to use Cauchy-Schwarz here. But I want a characteristic function in both of these. So I'm just going to square this, which does nothing. So well, maybe I should be a little neater here, more efficient in my handwriting. Okay, so here, same thing, except I have characteristic function h prime. It's a little bit challenging writing this, but I think I will be able to do it. Power of positive thinking. And again, if you simply don't have room, you don't have room. I'll think positively. Yeah, I do have room. Yeah. So it's Cauchy-Schwarz on. All right, so what is this equal to? Well, again, squaring a characteristic function does nothing. To integrate this characteristic function is just a measure of 0 to x. So it's x to the 1/2. So square root of x. Can't really do anything here except just integrate from 0 to x. Squaring characteristic function does nothing. Still 0 to x. Sense. We're actually almost done. So what have we proved? We've proved that absolute value of h of x over square root of x for x bigger than 0. So like I said, I want the limit. I want to prove the limit is 0. So I really should be doing limits, but I want to prove the lim inf really is 0. This is sort of assuming whatever. Get the point. So 0 to x. The absolute value of f prime squared is an L1. Just to be clear, this here is an L1. So f prime is an L2 is the same thing as saying the absolute value of f prime squared is an L1. So I'm going to use 7a with well, instead of little f, it's absolute value of f prime squared. So this limit here goes to 0. And that's a very nice, clever use of Cauchy-Schwarz inequality and absolute continuity, implying the fundamental theorem of calculus. Yeah. So, yeah, and that's that. I don't know too much about absolute continuity for higher dimensions, functions on a cube, on Rn. Yeah, and I actually looked up the definition of bounded variation on for functions on a cube in higher dimensions. I think you actually need to know the theory of Sobolev spaces, which is something, if you're interested in the theory of data science, you might actually study. I know when people want to prove something like universal theorems for neural networks, can you guarantee a neural network can learn a certain type of function? A typical thing to do is look at Sobolev functions, and prove that neural networks can learn all of these functions. People maybe even looked at bounded variation functions. Can a neural network always learn a function of bounded variation? Can a neural network always learn function that's absolutely continuous? Yeah, I actually am gonna I'll look that up and see if that's research has been done. That's a good question. But anyway, I'm guessing it has. We actually had I think it was a Maheshwari type colloquium where exactly that kind of topic was discussed. But anyway, all right. Well, so long. Take care. Bye-bye.